Assalamualaikum warahmatullahi wabarakatuh. This video is about presentation of case study PHY351. The title of this case study is Composite Material Uniting Strength, Flexibility and Versatility. It have 5 group member, which is me, Ahmad Izzat Iqbal bin Zaini, Farid Daniel bin Muhammad Fadil, Muhammad Firdaus bin Ilyas, Muhammad Imran bin Cik Murad, and Nurul Christina binti Muhammad Farid. This video consists of 4 parts, which is introduction, theoretical background, content of title, and the last one in conclusion. Let's go through to the introduction. Composite material are formed by combining 2 or more material that have quite different properties. The different material work together to give the composite unique properties, but within the composite, it can easily tell the different material apart. They do not dissolve or blend into each other. The example of the composite material is concrete, mud, brick, and fiberglass. Most composites are made by taking one material, which is the matrix, and having it surround fiber or fragment of a stronger material, which is the reinforcement. Engineers have many choices during the manufacturing process to determine what the properties of the resulting composite will be. Modern aviation has been primary driver for composite material, as it has great demand for material that are both light and strong.
Next, we're going to talk about the properties of composite materials. The first one is strength to weight ratio. One of the most remarkable features of composite materials is their exceptional strength to weight ratio. By combining materials with high strength and low weight, composite can achieve impressive structural performance while maintaining lightness. This property is especially advantageous in aerospace, automotive, and sporting goods industries. The second one is tailored properties. Composite materials allow for the customization of properties to meet specific application requirements. By carefully selecting and arranging the constituent materials, engineers can tailor composite to possess desired characteristics such as strength, stiffness, thermal conductivity, electrical conductivity, and resistance to corrosion or chemicals. This versatility makes composite suitable for diverse applications across various industries. The third one is anisotropic behavior. Composite materials exhibit an isotropic behavior, meaning their mechanical properties differ in different directions. By aligning the constituent materials strategically, composite can be designed to have different strengths and stiffness in specific directions, which making them highly adaptable to complex loading conditions. And the last one is durability and resistance. Composite possess excellent resistance to environmental factors such as moisture, temperature variation, and chemicals. This durability makes them ideal for applications that require long-term performance and protection against harsh conditions.
Hi, my name is Nurul Christina and I will now talk about the theoretical background of composite materials. The term composite materials, sometimes known as composition materials or simply composites, are referring to materials made up of 2 or more components, each of which exhibits a wide range of physical and/or chemical properties. When 2 or more fundamental elements are combined, a new material is produced. Those new material produced have properties distinct from those of the original components. Composites must be properly distinguished from material mixtures and solutions of solid for the constituent components to stay unique and separate within the final material structure. The new composite material frequently exhibits a variety of advantageous traits. Frequently, the composites are stronger, have a lower density, or they are more affordable than traditional materials. Commonly, composites are made up of 2 or more different components that come together to produce regions big enough to be thought of as a continua, which the basic components are are typically tightly fused together at the interface. This conclusion is supported by a wide range of both natural and manufactured materials, including mortar and concrete, reinforced rubbers, alloys, polymers with fillers, composites of align and chopped fibers, porous and cracked media, polycrystalline metal aggregates, and others. Individual fundamental materials, often known as constituent materials, are the building blocks of composite materials. The matrix, which also known as binder, and the reinforcement are the two basic kinds of constituent materials that are distinguished. To generate a composite, at least one from the basic kind of constituent is required. The metric phase maintains the reinforcement relative placements while embedding, encircling, and supporting them. The reinforcements add their unique physical and mechanical advantages, which improve the matrix qualities. The two phases synergy produces material qualities not seen in the constituent materials alone, and the designer can combine any number of binders and reinforcement in the most effective ways to create composites that are specifically tailored to their needs.
Strength of composite material. Composite material exhibit exhibition strength due to the reinforcement provide the constituent fiber or particle. The high tensile strength of fiber combined with the ductility of the matrix material result in composite with superior resistance to mechanical force. Compared to the traditional material like metal or plastic, composite material can withstand higher load before failure, making them ideal for the main structure application. Flexibility of composite material. Composite material offer significant flexibility in terms of design and shaping. They can be molded into complex shape, allowing for the creation of lightweight and aerodynamic structure. The flexibility of composite also enable the development of product with curved surface, improving aesthetic and functionality. Additionally, composite can be easily repaired or modified, adding to their overall flexibility and cost-effectiveness. Versatility of composite material. Composite material find application in wide range of industry due to their versatility, and they are extensively used in aerospace, automotive, construction, energy, sport and recreation, and many other sectors. Composite provides solutions for light aircraft, full efficient car, durable insulation wing to wing blade. The ability to tailor their properties to specific need make composite versatile and indispensable in modern engineering and manufacturing. That's all.
So the last part, we're going to talk about the conclusion. In this part, we're going to talk about why the many industry use the composite as a materials. Firstly is weight reduction. The composite improves the specific strength and stiffness. It helps to reduce fuel use or increase the acceleration or range in transport. It allows for easier, faster installation or faster movement of robot arms and reduce supporting structures or foundations. It also helps to improve the topside stability in vessels and offshore structures and buoyancy for deep sea application. Next is durability and maintenance. Composite don't rust. It also non-lubrication and don't corrode. It can increase the product lifespan by several times in many applications. Next is added functionality. Composite has a thermal inserter which is good for fire and blast protection or cryogenic applications. Composites also have the sensors, electronics and cabling can be embedded. Lastly is design freedom. Composite allows for freedom of architecture form. It also has many parts can be consolidated into one and stiffness inserts. It also can be tailored to suit the application by choosing the constituent materials and embedding extra functionality.